So today's problem set is from chapter 23, which was on electric potential. So let's take a look at the problems that we are going to go over, both for the recitation and for homework. So the first problem, the work done by an external force to move a negative 9.10 microcoulomb charge from point A to point B is 7.00 times 10 to the negative 4 joules. So you're given the charge and you're given the work done to move it. So that's an external force, which means it's a non-conservative force. If the charge was started from rest and it had 2.10 times 10 to the negative 4 joules of kinetic energy when it reached point B. So we've basically been given the change in kinetic energy. What must be the potential difference between A and B? So think of what you know about the work done by non-conservative forces and think about how that applies to potential energy and how that applies to electric potential. And that's how you figure out how to solve problem 4. Next, we move on to problem number 19. A non-conducting sphere of radius r0 carries a total charge q distributed uniformly throughout its volume. So think about the non-conducting sphere that we did with Gauss's law, how you solve the electric field for that. Determine the electric potential as a function of the distance r from the center of the sphere for r is less than r0 and r is greater than r0. So we're going to be doing indefinite integration here. So you're going to have your potential, you're going to integrate over dr first inside the sphere and then outside the sphere. And so you'll get a function of r plus c. And so you'll have C1 inside the sphere and C2 outside the sphere. And you'll be able to solve for C1 and C2 because V is set to 0 at r is equal to infinity, and B, at the boundary where r is equal to r0, the potentials need to be the same. So you're going to have the potential as a function of r inside the sphere and outside the sphere, but at the surface of the sphere, they're going to be equal to each other. So that's going to enable you to solve for the arbitrary constants that you're figuring out through indefinite integration. And then you're going to make a plot of V versus R and E versus R. You don't have to be technical with that. Just visualize how those look. And you should be solving for E first using Gauss's law and, again, integrating. So there's a bit of calculus in this one. Then we move on to number 30. Two identical positive 5.5 microcoulomb point charges are initially spaced 6.5 centimeters from each other. If they are released at the same instant from rest, how fast will they be moving when they are very far away from each other? And assume that they have identical masses of 1.0 milligrams. So you have the potential energy, and each carries a certain amount of potential energy, and that potential energy gets converted to kinetic energy as you're moving an infinite distance away. So you set the potential energy to be 0 at infinity, so it's going to be losing potential energy as they move, or each particle is going to be losing potential energy. And so they're going to be gaining the same amount of kinetic energy. So if you know what potential energy each charge has initially, and that's not that hard to calculate, then you know how much kinetic energy they have when they're moving very far away from each other. And since you know the mass, you can figure out the velocity. That brings us to number 34. 3-point charges are arranged at the corners of a square of side L, as shown in a figure. So you're going to need to look up the figure. What is the potential at the fourth corner, taking V is equal to 0 at a great distance? So you would need to figure out the potential at that point to each of the charges individually. And again, this is simpler than figuring out the electric field at that point because you don't have to break into components. You're just adding your potentials together. Then for question 50, the electric potential in a region of space varies according to that function. So it's a function of y. So determine the electric field. And so again, this is calculus. So you're going to need to take the derivative of v to figure out the electric field and to figure out which direction it's going in. Assume you're in an XYZ coordinate system. And that brings us to number 61, which is the last of the recitation problems. So an electron starting from rest acquires 1.33 kilovolts of kinetic energy in moving from point A to point B. How much kinetic energy would a proton acquire starting from rest at point B and moving to point A? Determine the ratio of their speeds at the end of their respective trajectories. So figuring out A is pretty simple. B requires a little bit of thinking, not necessarily a lot of thinking. But if you think about what's going on in the problem, you should be able to figure things out a little bit. And the units are given in kilo electron volts. So that should tell you something, about the potential difference from point A to point B. And you should be able to figure things out from there. So those are the problems you're going to work on in your groups, and one of you from each group is going to present a video solution by Friday. That brings us to the homework problems. So these are going to be due on Monday. So a uniform electric field, E is equal to negative 4.20 newtons per coulomb in the I direction. So it's the negative X direction the electric field points in. And so it's given in the figure. So you're going to need to look that up. The X and Y coordinates of points A, B, and C are given on the diagram. Determine the differences in potential, VBA, VCB, and VCA. So going from point B to point A, from point C to point B, and from point C to point A. Do you gain or lose potential, and how much? Then we go on to 26. 2-point charges, 3.4 microcoulombs and negative 2.0 microcoulombs, are placed 5.0 centimeters apart in the x-axis. At what points along the x-axis is the electric field 0 and the potential 0? So put the 3.4 microcoulomb charge at the origin and the minus 2.0 microcoulomb charge at x equals 5.0 centimeters. And so then at what point is the electric field 0, or what points, and the potential 0? So you can have multiple answers for both. For number 49, the electric potential between two parallel plates is given by, you see the equation, and it's a function of x, with x equals 0 taken at one of the plates and x positive in the direction towards the other plate. So one plate is x equals 0, and the other plate is going to be to the right of that one. What is the charge density on the plates? So you're going to need, given the voltage, you're going to need to figure out the electric field between the plates. And once you know the electric field, you should be able to figure out the charge density. And that brings us to number 57, the last of our problems. Many chemical reactions release energy. Suppose that at the beginning of a reaction, an electron and a proton are separated by 0.110 nanometers, and their final separation is 0.100 nanometers. So they get closer. So the electron moves towards the proton. How much electric potential energy was lost in this reaction in terms of electron volts? So you figure out the potential energy at one location and the potential energy at the other location. You'll probably get your answer in joules first, but then you convert that to electron volts, and that's your final answer. So those are your 10 questions. Again, 6 for the recitation, 4 for homework. Good luck. If you have any questions, do not hesitate to email me and ask for help.